Hey everyone, I'm Karl Weinmeister. I'm with Google's Developer Relations team. I'm excited to be here today to talk to you as part of the ML Summit. Let's go ahead and get started and check out my presentation. What we're going to cover today is time series forecasting using the Google Cloud Platform. So in this session, I hope to introduce you to some of the concepts around time series forecasting, kind of a unique area within the AI ML field, as well as introduce you to how to do it on the Google Cloud Platform. Let's get started. We're going to start out with some of the challenges in forecasting. Why are we doing it? What's the benefit of it? We're going to cover what's unique about time series data. We'll talk about different ways to model time series. We'll look a little bit at tooling to accomplish our goals. And finally, we'll do a brief demo. So why forecasting? It's something that since the beginning of time, folks have been very interested in. It's predicting the future. So it's a very important problem. It derives a lot of value for the business, and it's challenging. The conditions are always changing, the world's changing, and so we want to be able to use any signal we can from past data to tell us a little bit about what might happen a step or two or three ahead. And that's why we're going to look into time series forecasting today. So there have been lots of studies on different types of data used in AI ML problems. And time series data consistently is one of the top types of data to be used in business problems. Structured data, or your typical tabular data, in databases is probably the most common with the most value. And time series follows just after that. And then you start to see other types of data used in business problems. Let's talk about some of the challenges with time series forecasting. And so in this presentation, we're going to look at both classical methods, or the kinds of methods using statistics that have been used for quite some time, and we're going to compare and contrast those to machine learning-based methods. So classical forecasting methods can be very good at what's called univariate time series problems, or time series problems with one variable, tracking one thing over time. And you can see some of the different ways in which classical forecasting methods are very good. One is providing a probability distribution of the forecast. So you can derive a confidence interval for your forecast to not just see what the expected value is, but the range of values. You can also infer seasonality in your data. Another thing you can do is infer outliers from your data, right? Because you have confidence intervals, you can kind of look at wherever your data starts to go out of those confidence intervals, you've detected some outliers. And finally, classical methods there are some great techniques for handling seasonality, for decomposing a time series into trend components, into seasonal components, and even multiple layers of seasonality. But there are some problems in which neural networks used in machine learning can definitely help what we've seen using statistical methods. So ML can be great at multivariate time series problems. So if we're tracking multiple variables over time, and there are relationships between those different variables. So for instance, maybe what we're trying to do is track store traffic over multiple stores at the same time. And maybe there are relationships between those different stores. There are traffic patterns where if more people go to one store, they are pulling away traffic from another. There are the relationships that a neural network will find between each individual data point as you track it over time. Another area where ML can be great is around cold starts, where you don't have a lot of historical data and you're trying to predict something quickly after you've started your series. Noisy and sparse data sets, which are super common. If you've got some outliers, some gaps in your collection, those can be handled pretty well with machine learning. And finally, because it can handle multivariate time series, you can also include metadata about whatever you're tracking. Like so for instance, if you're tracking some data point, you might have like geolocation data around where that data was collected. It's just something you might want to include into your time series to kind of provide some additional signal when building your model. Some other ways in which machine learning can be great is predicting multiple time steps ahead. Also, there's less retraining needed than statistical methods. So a model that you build will hold its value for longer than some of the statistical methods without having to retrain with the latest data. And finally, there's been a lot of great tools out there for building machine learning pipelines, and time series based machine learning models are just another type of model. So you can plug it into a pipeline like TensorFlow extended or Kubeflow, et cetera. So let's look at one example of a time series problem. And there are so many of these. This is just one. So here we're looking at an example that was on the Google blog around predicting energy production. And so this was a case where if you can predict wind power output ahead of time, you can make a commitment to the power grid, and that increased the value for the producer and the consumer of that energy. Just you have more predictability, you can make better decisions with this information. And this is a great example of taking advantage of the benefits of a machine learning based approach, where you're predicting multiple time steps ahead. You have multiple exogenous variables or variables outside of the main thing you're tracking. And you have noise, you have lots of sensors and many data points, and you're trying to put that all together in a model. That's one example of machine learning applied to a real-world time series problem. Okay, so now let's talk about how to solve a time series problem. So first of all, just basic question, what's a time series? A time series is a data set that has a couple dimensions. One is time, you see here on the x-axis. The other is whatever data we're trying to track. That's it. And we're just recording that data at consistent intervals over time. And a time series can often be decomposed into components. So here we see an example at the top of some data where you can sort of eyeball that, you know, there's a repeated pattern and there's also a trend line. And so there are some approaches to pull that apart so you can see the long-term trend, you can see a repeating seasonal pattern. And then what you're left with is the residual. That's what's not explained by either the trend or the seasonality. And ideally, that residual is, you know, as small as possible if you've, you know, if we're able to explain the model as best we can. Okay, so let's differentiate a couple terms. If we're talking about seasonality and versus a cycle. So a seasonal pattern is when you have a known recurring pattern to your data. For instance, certain days of the week are busier in a call center. So, you know, as we're looking at the data over weeks, you know, Mondays are a busy day because there's some pent-up demand. Nobody's able to call in over the weekend, and then Monday, a lot of calls come in. Or, you know, maybe certain days of certain weeks of the month exhibit patterns, holidays, et cetera. So that's seasonality, where we can tell ahead of time what pattern we might see. Whereas a cycle, there are rises and falls, ups and downs, but they're not predictable. So an example of that is a business cycle, where, you know, you might have boom and bust periods, and there are cycles, but they're not something we know ahead of time. So we talk about cycle seasonality here. It's something that's known. Okay. So another thing that is important to talk about time series data, and this is a core concept in modeling, is it's called IID. So it's an assumption that data is independent and identically distributed. So let's think of an example of that. So a coin flip is a good one. So each time you flip a coin, each flip's independent of the previous one. And secondly, each flip has an identical probability distribution. So that means that, I flip it, every time I flip it, it's always a 50% chance. So let's think about time series data. Is it IID or not? Well, it depends. So in some cases, it's not. So you can see here that, this graph on the top right side, right? You're seeing an increasing trend over time. So we want data that we model to be, it's called stationary. So that means that the statistical properties hold over time. The mean, the variance, et cetera, kind of is constant and not changing. So there are things we can do to our raw data to help it be processed in a way that we can use in a machine learning model, such as detrending or differencing. So detrending might be where you see that graph that's going up and to the right. If we subtract that trend out of it, then you end up with a graph that looks like the one in the bottom right. And then differencing is another approach where we can remove some seasonality. So maybe what we could do is subtract last year's data point from this year's data point to sort of even that out, right? So generally, statistical methods require your data to be stationary. And as far as neural networks, sometimes there's different viewpoints on whether it makes a difference or not. But just something that you should know with your raw data, you might need to apply some processing to get into this form. Okay, so the next thing you might want to think about is how to transform your data to, after it's been made stationary, into a format that you can use in machine learning, right? So on the left side, imagine that you have measurements for each month of a certain variable, okay? And then on the right side, what we're doing is we're creating lags of each of the variables, right? And we're kind of saying, on the right side, the actual target was what it was. And then as you go down each month, we're kind of saying, what was the value a month ago, t-1? And then what was the value 2 months ago? And so what we're going to do with that information is we're going to use t-2 and t-1 to predict what happens today. Okay, so this is where we learn from the historical data. We look at what is the impact of past measurements on the most recent measurements. Okay, so we're doing a little processing to change our data in a way that we can learn from it. And we have labels, which are the actual data points. Okay, so you're doing traditional machine learning that's not with time series, where time is not relevant. You split up your data into train and test data sets. So for instance, if it's a 75-25% split, we might randomly split up our data like this. And by the way, if you're not familiar with this, the reason we do that is we want to test on data we've never seen before. So it's kind of cheating if we train on data and then we check the accuracy of our model on that very same data. Let's apply it to some different data to just really make sure we have an objective perspective on how it's doing. Okay, so with time series problems, you need to use a chronological split. So you want to take, say, the last or most recent 25% of your data to train your model. Okay, and one other more advanced point as far as testing your data, there's a concept called cross-validation. So again, in traditional non-time series models, you might use something here where you take folds of your data. So you don't just randomly split it. You say take the first 25% and make that your test data, and the other 75% your trained data, and you evaluate it, and you get a certain accuracy result. And then you kind of move that fold along, and you say, let's use a different 25% as our test data, and then you get a different evaluation result, and you can kind of combine that all together, average it, and get a good view of the accuracy across the whole data set. So with time series, you can't exactly do that, but what you can do is something similar here, where you can test in different folds on the most recent slice of the data. So just wanted to mention that as far as how to evaluate your model. Okay, so now we've talked about some of the foundation, how to evaluate your model, and then how to split up your data. Now let's actually talk about how to build some time series models. Okay, so this is the only slide with math on it. I just wanted to present in one slide what a common statistical method that you may have heard of called ARIMA, what it's doing. Because when you're applying a machine learning approach, you want to have a baseline. You want to compare how it's doing against a method like ARIMA. So let's look into this and just explain it briefly. So let's look at these different models that are all very related. They'll layer on top of each other. So the first one we're talking about here, ARMA, consists of two different methods, right? You see it's made up of two pieces, autoregressive and moving average. The first part, autoregressive, what we're doing here is we're creating a regression where we're applying a coefficient to the previous values, one historical data point back, two historical data points back, figuring out what that optimal coefficient is for each of those. And then the moving average is similar, except it's actually doing a different approach where it's looking at the error from the past and then adjusting based on what that error is. So kind of not directly using the past value, but using the error from the previous prediction and applying a coefficient to that. Okay, so this ARMA equation is combining both those together. And you see there are two parameters, P and Q, and that's telling us how many data points back that we want to go, right? So is one data point back just simply looking at a last one good enough, or do we need to go 3, 5, 10? How far back? And generally speaking, the further you go back, the less impact it has, except for when there's seasonality. So picture if you're looking at monthly data, you'd see last month's data is important, 2 months is important, then it starts to sort of be less relevant. But then T-12, last year's data point, might actually be an important one. So those are some of the parameters that in a statistical model you might look at. Okay. The next layer on here is called ARIMA. And the only difference is it adds one more variable for the differencing. Remember I talked about before where you can subtract one value from the past to kind of make the data more stationary. So you can pass in this parameter D that tells you how many times do you want a difference to even out that data. The final thing I want to mention is you might hear of SARIMA or seasonal ARIMA, and it's ARIMA, but it adds one more layer of seasonality. So you would create an ARIMA model, and then you would also add a seasonal component. So, you can see this parameter where you might have a lag of, say, 12 months for monthly data. And many common models you see there below, random walk or exponential smoothing, can be expressed in terms of these parameters for ARIMA models. Okay. So I know that was a lot of information, but again, that helps just at least provide a point of comparison with the neural network models we're going to discuss now. So we're going to talk about two different types of models that are popular for time series data, LSTM and CNN. There's another one, sequence to sequence models, that are also popular. We won't get too deep into that one. So all of these use a neural network. And if this is a little bit of a new concept, let's just briefly walk through that. A neural network consists of an input layer. These are your features in the model. And then you might have multiple hidden layers or nodes in the model. And eventually it comes together to produce an output, or you see here the output layer. So that would be, let's say in our input layer, the different time series measurements. The hidden layers allow for different combinations of those features. And that's where kind of like if some features have interesting relationships, those are going to be discovered in those hidden layers. And the output layer is where, say, the next prediction gets outputted. Okay. And so we're going to look at different forms of these neural networks and how they apply to time series. Okay. So RNN, or a recurrent neural network, is much like a traditional neural network, except you have extra information passed in, not just the input values, but you see here in this diagram, V is passing in some signal from the past data points. So as you're computing new information, you're also pulling in information from the past to make that next prediction. There's an important improvement on RNNs called LSTMs that it's a very common approach. And there are many variants of this, many improvements on RNNs. So we're just talking about LSTM today. And some of the reasons that LSTM improves over an RNN is that there can be a problem in, it's called vanishing gradients. And what can happen is that that signal, when there's a very low coefficient, it starts to kind of really quickly go away, and you lose some of that signal in the model. And that's where you see in natural language models, sometimes you're not able to go back many words back because of that vanishing words problem. So you're only able to look at kind of a few words at a time. And that was one of the issues with RNN, that signal starts to go away. So LSTM has some improvements. You see some of these logic gates. We're not going to go through this in a ton of detail, but the key is that it learns what the important information is and what can be forgot. So it has sort of like remembering gates, forgetting gates, and it also has, you see here, not just a multiplication, but it has some addition of some of the values in each of these units. And that avoids the problem of if you have a very low number and you're multiplying it times a very low number, it quickly goes away. So here we're applying some different mathematical properties to the data so that that signal's preserved a little bit better over the life of the neural network. Okay. Then in CNNs, or convolutional neural networks, are very popular. And there's a kind of unique variant called a one-dimensional CNN that's used. So typically you might see in image problems, like say a two-dimensional CNN. In time series problem, one-dimensional is pretty popular. And let's kind of just walk through a little bit of the thought process here. This is one possible architecture in building a CNN. So we have our input data here, and you can see the number of measurements kind of across the top here. So think of that as, here we have 4. There's 4 different things that we're measuring at every data point. The kernel size, think of that a bit as the window that we're going to slide along the data that we're going to use as an input to our model. And then we have sort of the whole length of the sequence, all the data that we're going to train on. Okay. So then what we're going to do is we are going to apply a filter to the data. So we're going to take some of these squares, some of this window that we're looking at, and we're going to apply a mathematical property to it to kind of shrink it, to kind of get some of the signal out of it, but without memorizing the whole thing. And so we apply these filters. And here, we have 3 filters. So this is where there's a little bit of that discovery, where a larger number of filters gives you different transformations that you're applying to that raw data. Okay. Another thing you might do is apply a pooling layer. So this is, again, another way to kind of get the key part of the signal without memorizing the data. So you might find the maximum value, the average value from within this window here, and then shrink it further. Then you might do something like flattening the data, where you put it kind of stacked up in a one-dimensional array. And then finally, you're going to apply a function to the final output layer. And so you might shrink it to the number of time steps ahead you're predicting. Maybe you're only predicting the next data point, so you'd have one. Maybe you're predicting 3 months ahead, and if it's monthly data, you'd have 3 of these. But this is just at a very high level, trying to walk through, if you're creating a CNN, how that's going to apply to time series data. Okay. So we've looked at some of the different neural network architectures. Let's look at the Cloud AI platform and how some of the tooling can help build a time series model here. So it all starts with the use case that's outside of the tooling, and that's going to drive the first part of data science, where you're prototyping, you're figuring things out, you're training some models. So the AI platform provides you Jupyter notebooks, serverless training, models that you can build, and access to GPUs, TPUs, all kinds of hardware to solve what you're trying to accomplish. Once you've built a model that you trust and you want to start to put into production, there are MLOps capabilities. So you might implement something like a pipeline that would, on a regular basis, extract data from a data source. Especially for time series problems, retraining makes a lot of sense. Gather the latest data, retrain your model, check the accuracy of your model, and then redeploy your model. You might want to put all those steps into one pipeline. And that's basically it, where you're using some of this tooling to train in the cloud, scale up your job. And then finally, once you're done training, you might want to host your model into the AI platform prediction service. And that gives you an endpoint where you can use your model and handle all the different requests coming to it. Okay. All right. So let's now do a brief demo. If you're interested in trying it yourself, you see a link here, bit.ly/time-series-code-lab. And this is a multi-part time series workshop that you can run yourself and learn a little bit more about what we discussed today. So let's take a look. So if we click here, I'm going to briefly show what the code lab looks like. You'll see and a little bit of a brief introduction of the concepts we talked about today, and then you'll see the different steps. Okay, let's just dive right in ourselves. What we're going to do in this lab is we're going to create a notebook server in the cloud, and I've already got it running today. And that will allow us to prototype our code. So in this particular example, it's a 3-step set of notebooks where we're going to do some predictions of vehicle sales. Okay, so you load up this notebook. We first start out with data exploration. This is always key. Let's look at our data. Let's look at the trends, and that'll help guide us, right? So we install some packages, and I'm going to skip over some of this stuff that's not key to our brief overview today. Just kind of configure some things. We're going to load some data, and let's take a little bit of an exploration of the data. So we are trying to predict vehicle sales, and we have one other variable. We could include a lot more in the model, but just to keep it simple, we're including unemployment rate. So we're kind of look at vehicle sales as a function of past sales, as well as how the economy is doing, to see what kind of impact that has. So we can plot the data, and I'm going to zoom in just a little bit so it's easier to read. And I'm going to pull this out of the way a little bit. And so here's where we see kind of the trends here. Okay, so we've got in green vehicle sales, and in blue the unemployment rate. Okay, and this looks like a tricky problem to solve because we don't really see that the blue line is ahead of the curve and prior to is making a change in vehicle sales before they dip. You notice that they do, there's clearly a relationship, but do we know ahead of time if unemployment is driving the vehicle sales, right? So it's a little iffy whether how much signal we're getting out of that variable. Okay, but we do know that they are, they're very correlated here. So, you might review the data a little bit. You might explore seasonality. Here in this particular data set, we're going to look at each month. We do see some differences per month where, you see that, July and September, we do see some, max values getting a little bit higher. But over time, on a monthly basis, it is fairly common. So here's where you can use some Python packages to automatically decompose the data like I showed in the presentation. So this is in the stats model package. You can run seasonal decompose, and you see here we're looking at a 12-month period. The trend is not super clear here in this particular data. We do see some seasonality, and this is able to give us a little bit of insight in our data. So this was just kind of a quick view of how we might graph our data, we might look for trends before we actually build a model. Okay, so the second workbook here, we actually get into modeling. And I won't get too deep into some of the specifics, but I want to show you some key things that you get into here. Okay, so the first thing is you can remove some outliers. So if you look at our raw data here, sometimes you might see that there's some variables that, 1 month was just way off. So we're going to learn in this notebook how we can apply some techniques to kind of smooth that out. And then you see that just as we train our model, we can hopefully not train on some of the noise, okay? And that can help our accuracy a little bit. And then this notebook covers some of the scaling and transformation of the data in a way you can use it for time series. And we're not going to look at all this code here, but that's all in this code lab. So let's actually look at one of the models we discussed. And for the model itself, it's not a ton of code. So that LSTM model, that remember that is one of those recurrent neural network models. You define it as a sequential model in TensorFlow. And here all we're saying is we're going to create an LSTM layer with 32 units. We're defining the input shape. And then our output layer is just set to the number of output steps. So we, at the top of this notebook, we say, we want to predict 3 months out or whatever. And so that's it. That's what it takes to compile this model. So you create the model, you train on it, and you'll see over time, as you train it, notice this loss starts to go down as we're gathering more and more of the pattern from it. And this is a simple data set that we're able to train completely within this virtual machine where the notebook server is hosted. But we could use cloud training and for larger jobs. And you see that on the next notebook. Okay. So what we do is we build our model, and then here's where it gets interesting. We're going to see how accurate it is. So here we're predicting several steps ahead, and we're going to look at some statistics here on the R squared, which is how much of the variance of the model is explained, how much of the variance is explained by the model, and then the mean absolute error, MAE. So that's basically the average error in each of our predictions, okay? And so remember that if the mean sales were somewhere around 12 million, I believe, somewhere around there, 15 million. And so its average error is off by about 500,000. So let's look at blue was actual, and then the dotted orange line is what we're predicting. And remember, we're predicting multiple time steps out. So here we have a graph for each of the different time steps. So we're saying 1 month out, how close were we? Well, we predicted pretty well. Let's look, 2 months out. Again, some of these trends hold, a pretty good R squared value, and so on and so forth. So we're basically comparing, what the values are 3 months out versus what they actually were 3 months out, okay? So the next thing, we do the similar thing, and I'll just kind of briefly show you. We do this convolutional neural network. Just like we described in the presentation, you create your network, You might specify how many filters, what the kernel size is. You might apply some pooling, you flatten it, and then you have your number of output layers. Again, there are more things you could do. I'm just showing a simple model here. Again, we're going to train. I've found that the CNN is faster than the LSTM in training, and depending on the data, can often provide better results. So we're going to predict here as well, and we show some of that. And then another cool thing we do here in this lab is we ensemble the models. So one thing you can do is combine multiple models together. And sometimes, if they have diverse approaches, you kind of get the best of both worlds where they might improve on each other. And so it's just showing how you can, here we're just taking a 50-50 combination of the values and seeing what kind of accuracy we're getting. The last thing that this covers is statistical models. So if you're curious about how to use the statistical models, this notebook shows how to use the stats model package, builds the models, and then compares them. And you can kind of, again, see how it's doing, versus the machine learning model. Finally, you could even combine the machine learning approach with the statistical approach, and you'll see that at the bottom. Okay, the final thing I want to show you is how to train in the cloud, okay? So if you're working with a larger amount of data, maybe you're working with data to the hour or minute or second, or you have a whole bunch of different measurements for each time step, you might want to do something like this. And so this notebook is all about how to train in the cloud. So we'll kind of skip through some of the same stuff about how to transform the data and just show you briefly what some of the commands are. How do you do this? So what we're going to do is create a model file, basically a Python file with our training code. And you see here, it just got a main method, and we're going to read our input files. We're going to create a model just like I showed you on the past notebook. And then when we're finished, we export the model to a storage bucket so that we can get our model and access it, okay? So we simply print out this model file, and then we'll just skip ahead a little bit, and we submit a training job. So here we see the Google Cloud AI Platform command line, where we submit our job using the training code and the bucket location we want to put our model, the version of Python, things like that. And then it's going to run in the cloud, and you're going to see the result of your training job. You can go to the user interface, or you can actually see the status here by running the describe command to see how it's doing. Okay, so that's the training part in the cloud. And we have, the command line here, but we also have SDK. So you could run this with Python code as well. So you might monitor your job. The next thing I want to show you is how to make predictions with it. So we have a prediction service as well. So using the models command, what we would do is create a model, and then we would simply version that model. We would pass in the trained model from the training step, and now we've got a REST endpoint that we can get predictions with. And so here, I'm just going to, again, do this from the command line. I'm running gcloud AI platform predict, accessing the model, and passing in a few items that I want to predict with. I parse the output, and then I've got my prediction. So in the end, what we're doing is we just take a data point. This is kind of showing end-to-end how to connect these things together. And we have the predicted sales for a given month and what they actually were, and kind of combining those. So this is all going to be in this set of notebooks. Okay. So that concludes the demo. I'm just going to go back here. And if you want to see the URL again, bit.ly time series code lab. And I hope you enjoyed the presentation. We covered time series concepts, the different AI models to build them, and finally some tooling so you can learn it and do it yourself using the code lab. Thanks again.